Hey friends, Ben again. This is a video for the differential equations class, and we are looking at what to do when you have repeated eigenvalues when you're solving those linear homogeneous systems. But then I'm also going to try to slip in the notion, at least, of what you do for undetermined coefficients. Okay, that seemed like the easiest thing to kind of slide together there. So let's look at what we're doing here. I would advise you to get the notes, which I will have linked to in a PDF next to where you got the link for this video. It's easier to follow along if you're kind of following along with the notes there, okay? Additionally to that, it would be pretty useful if you can keep in another window or print it out or something, the actual assignment we're going to be working on, because I'm going to make reference to the theorems and definitions and stuff that we've got there. I don't feel like writing them twice today. I'm in a little bit of a rush. So bear with me. Let's get our iPad going. 1, 2, yep, it's going to go. Yay. All right, so repeated eigenvalues and then undetermined coefficients. All right. So here is the kind of problem that we're looking at. As usual, we've got an x representing a vector valued function, and we have it in one of these homogeneous systems where it is just basically saying that you've got x prime equal to ax, okay? And as we've seen before, the thing that we do with that is to go looking for an eigenvalue. Now, I don't want you to have to do your eigenvalues by hand all the time. So jump over to Colab or whichever other thing that you might be using and find out your eigenvalues on this one. And oh no, turns out that there's only one eigenvalue, lambda equals -3. And it'll come along with an eigenvector of 3, 1. And you can figure that out the same old way as you have before. I will tell you that I went ahead and did this on Colab, and when it popped up, I could look and see on the column that corresponded, well, I'm sorry, on the first column, I could see that it looked like 3, 1 was going to be there. It was like 0.9 something and 0.3 something, so I had to kind of guess. But then after I guessed, I thought about the matrix that we would make here by taking our A and subtracting, well, yeah, subtracting -3 from the diagonal, which is to say that you would take your 3 and add 3 and get 6, and your -9 and add 3 and get -6. And so I could see that that 3, 1 was going to be perpendicular to 6, -18. So I knew that the dot would turn out to actually be 0. So that was how I got that one. I didn't actually like go through all the formal work of figuring it out. So, right, once you've got that, the new thing that we're doing is dealing with these generalized eigenvalues. That is to say, if you've got the case like we do here of having your lambda have a multiplicity of 2, you may sometimes be able to get linearly independent eigenvectors. We're going to do one of those examples here in a second. But sometimes you may not, and this is what you do when you can't. What you do is you go ahead and take your a minus lambda I here, and you look for a vector which, when you multiply it by that, you get your eigenvector, okay? So the notion of that is that when you take the a minus lambda I here and multiply it by that vector twice, you will end up getting the 0 vector. But multiplying it just once, you would get the 3, 1. So setting that up there and multiplying out, on the top you'll get this 6x1 minus 18x2 is equal to 3. The bottom, you'd get 2x1 minus 6x2 equals 1, which is just a multiple of the same equation. So that is what we've got to solve there. And we can go ahead and solve for the x1. You could have solved for the x2. Either way, it's fine, But once you get down here, you have one equation with two unknowns. You have to make a choice. I'm making the choice of x2. And if I get to choose x2, what do I choose? Every time I choose 0, because 0 is the nicest number to calculate with. You add it, you multiply it, it's great. I sound like I'm doing an advertisement for 0. Oh, gosh, sorry. Well, in any case, though, then our first setup we had here gave us our first solution. Okay, it's just the eigenvector multiplied by e to the eigenvalue t. Now, the next one is complicated. It's kind of a pain, actually. So you're going to construct more of these by taking the eigenvector, and then saying t e to the minus lambda t. And then you'll add onto it this generalized eigenvector that you got times the e to the lambda t. Now, if you had a third one that you had to do here, then you would have the 3,1 times a t squared e to the minus 3t, and then you'd have the 1/2 0 times a t e to the minus 3t, and then you'd have whatever the third order thing ended up being multiplied by e to the minus 3t, okay? But for us, we just have that. Now here's a fundamental solution set, or alternately the general solution. Notice with the general solution, you want the C2 to multiply by the whole thing, not just part of it, okay? So that's what we're doing here. I want us to look at another example because you can run into something like this, okay? So this, oh, and I forgot to write my X because I'm a silly head. All right. So this one here, same sort of setup. We take our matrix, and because we don't want to work harder than we have to, we jump over to Colab. We find out that lambda equals 5 is one of the eigenvalues, and then lambda equals -1 is the eigenvalue with multiplicity 2. That is to say, there's going to be a lambda plus 1 squared if you were moving out, or if you're writing out the characteristic polynomial. But for using Colab, we'll just see that the lambda value of -1 occurs twice, okay? So with regard to that, we'll look right here, and on the Colab, I think it said something like 0.7 and -0.7 and +0.7 on this vector here. And, I could tell that they all have the same magnitude, and they can't all be 0, so they must all be 1, because 1 is the second easiest number, all right? Then we've got to deal with, then for that one, we can just duck it in to our solution set, no problem. Then for lambda equals -1, we will get one solution. Well, sorry, we need to get solutions going on here, but we have to get the eigenvectors. So you go ahead and take your matrix and subtract -1 from the main diagonal, and then you've got this 2, 2, 2 in the diagonal. And when you take and dot your 3 vector here with that row, you're going to get this 2x1 minus 2x2 plus 2x3 equals 0. And if you check the other 2 rows, they are just the same thing or the negative of it. So this means we could solve for one of those. It doesn't matter which one. And you can say x1 equals x2 plus x3. And wow, I'm adult. I don't know if y'all caught this, but I dropped my negative there. So that should actually have said minus instead of plus. And I'm gonna make that the same thickness. All right. So the key thing on our choices, though, is we cannot choose them both x2 and x3 to be 0. Because if we do, then we end up getting the 0 vector. That's not an eigenvector. Okay? So we have to choose one of them to be 1. So for this first one here, I chose to make my x2 be 1. And that said, and then I went ahead and chose my x3 to be 0. And that said that my x1 had to be 1 minus 0, or just 1. Then for this one here, I chose my x3 to be 1 and my x2 to be 0. And that means that I should have gotten a negative 1 right here. And so I will go ahead and repair that in all of the copies that we have down here. Okay. So once you've got that, if they're linearly independent, then you can just go ahead and make more solutions, right? And so our fundamental solution set will just be those three things. Our general solution will be a C1 plus and a C2 plus and a C3 plus. So kind of like we've done on other things. So this, if we happen to get one that has more variables than you have equations, then you get to make a choice. And that choice will then inform the other parts of it. In this case, because we had two more variables than we had equations, that meant we got to make two choices, which meant we got two eigenvectors. All right. So this one here is something that's kind of got a common form that you'll see a lot. Oh, wow. Look at that. I forgot to write down what my initial condition was. So I have to look back here. It looks like it was 1, negative 4, 1. All right. 1, negative 4, 1. Sorry. Okay. So our setup is like before, but now we've got an initial condition to go with it. So we're trying to figure out our eigenvalues, and we can go to Colab and let it do that for us. Or if you have what's referred to as a triangular matrix, that is to say, it only has numbers on and above the diagonal, or it only has numbers on or below the diagonal, if the other part of it's all zeros, then because of the way the multiplying out the determinant will work, you are going to get the eigenvalues just listed right there on the diagonal. Okay, so if you see one like that, do it the easy way there. Okay. But now we're going to go ahead and figure out what our eigenvectors are by hand. Okay. And so you have to subtract the 2 down that diagonal there, and then you've got this sort of thing. And so we're going to have this 1, 6, and remember that those will go with the x2, x3. I kept screwing that up when I was writing it down. I just messed it up over and over again. But it's x2 plus 6x3 has to be 0, which tells you that your x2 is going to be negative 6 times your x3. But because the other part, the 5x3, the x3 has to be 0. So that tells you that both of these guys have to be 0, and you're only allowed to choose this one here. You can't have a 0 vector for an eigenvector, so you have to choose something else. So choose 1. Second best number, right? I think I've said that like a bunch of times now. Then in getting the generalized eigenvector down here, we're going to take the same matrix, and the nice thing about being able to do these things electronically, I didn't have to write it all down. I could just copy it and pop it over to the next place. but it's the same matrix times x1, x2, x3. But now instead of setting it equal to 0, 0, 0, we set it equal to the 1, 0, 0 that we just got. So when you multiply out, your x1 plus 6x3 has to be equal to 1, and your 5x3 still has to be 0. So that means this one here, the x3 has to be 0. And when we plug it in to figure out the x2 has to be 1. And so this choice up here at the top, you could choose whatever you want, but 0 is the easiest. So I went ahead and left it as the 0, 1, 0. Okay. And then finally, we'll take same matrix situation, set it equal to the 0, 1, 0. And that means your x2 plus 6x3 needs to be 0, but this time your 5x3 needs to be 1. Okay. So if that's the case, then that says that your x3 has to be 1/5. No way around it. And then plugging that in here, we're going to find out that our x2 has to be -6/5. And then your x1 can be anything you want, and I always choose 0. Okay. Now you have your generalized eigenvectors. Well, you have your eigenvector and then your two generalized ones. And we start constructing solutions. The first solution is just eigenvector times e to the lambda t. So 1, 0, 0 times e to the 2t. The next one will have that 1, 0, 0 times a t e to the 2t. And then the first generalized eigenvector times the e to the 2t. Okay. Then your third solution is going to have the 1, 0, 0 times t squared e to the 2t, and the 0, 1, 0 times a t e to the 2t. See how every time it just bumps up one power? And then the new thing, the 0, -6/5, positive 1/5, gets multiplied by e to the 2t. Okay, so those are your three linearly independent solutions. And then we're done. We don't have anything more to do. La, la, la. No, no, no. Oh, no. We have an initial condition, right? So this took up our whole page. So we have to go to the next page. So for this, I went ahead and wrote out the general solution. That's a mess, right? But we knew that we're plugging in t equals 0. That means that this goes away, and that goes away, right? Which now makes our choices of zeros pay off like big time. Because now we've got C1 times this 1, 0, 0, C2 times the 0, 1, 0, C3 times, okay, this last one doesn't pay off all that much. But that first choice there, if you write this as an augmented matrix, you'll have the 1, 0, 0 going across the top there, and that 1, that tells you C1 had to be 1, okay? Then writing out the second row, the 0, 1, -6/5, and then -4, and then the third row, the 0, 0, 1/5. So in going across here, I multiplied the bottom row by 5 to make it nicer, and then I had 1, 5. That tells me my C3 has to be 5. Boom. But then for this row here, I got it by multiplying this row by 6 and adding it in there. And when I did that, I ended up getting this 0, 1, 0, 2. That tells me my C2 has to be 2. So C1 is 1, right? C2 is 2, and I went ahead and distributed those through there. And C3 is 5, and I went ahead and distributed it through there to the vector. Now, if you want to, you can collect the whole thing together there and have it as one vector valued function. I got tired of writing, so I wrote the e to the 2t out to the end. If you don't want to do it that way, you don't have to, but so essentially, these are a lot like what we did for undetermined coefficients when we had something that was one-dimensional and higher order. However, it does have these things here getting really nasty. It's because everything's based on eigenvalues and eigenvectors. So, all right, one more thing. So here we're going to take a look real quick at doing undetermined coefficients. You've already done undetermined coefficients. When you do the undetermined coefficients, you just have to remember that now the coefficients of the functions are going to be vectors. Okay, so if we look at what we have here, we can figure out the x sub h the same way as we've been doing before. Okay, we figure out the eigenvalue and the eigenvector, and then the x sub h is just going to be c1 eigenvalue times e to the c1 eigenvector times e to the eigenvalue t, and then c2 e to the 0t. Well, e to the 0t is just 1, isn't it? So I don't need to actually write that down. So it turns out I was right. I thought I was mistaken, but it turns out I was wrong about that. So yeah. Now figuring out the x sub p, the thing that we see is that we have a constant over here. So normally we would just say, all right, I've got a b1 and a b2, and I'll just figure out what I need to have in order to make this work out. But because we have lambda equals 0 occurring in here, that means that we have to build things up. And so we'll have to have an a1, a2 times t and a b1, b2. Okay, these are not eigenvalues and eigenvectors, so you don't have to build them in that really bizarre and painful way. But so that means my x sub p, the form of it will be like this here. Okay, so if I took the derivative, because we've got an x prime over here, I would just get a1 and a2, no sweat. But if I calculate the other side of it, there's some sweat. So I'd have to take a matrix and multiply it by this a1t, blah, 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 blah. Anyway, I have to multiply by a matrix, and then I have to add a vector afterward. So when you do that, you end up with this kind of messy thing and this kind of messy thing. And remember that this needs to be equal to this. Okay, so this requires more room. We go to yet another page. So what I did here was to just copy those down, and I copied them down into different spots. Okay, so copying the first one down, if you go ahead and put the things with t's together, you can see that on the left-hand side, you have a1 minus a2 quantity times t. The right-hand side didn't have any t's, so think of it as 0t. In Calc 2, in theory, you have seen equating coefficients as your technique of doing partial fractions, okay? So if you have two polynomials on either side of an equation and you allege that those polynomials are equal, their coefficients have to be equal. So that means this needs to be 0. So that means a1 has to be equal to a2. So we keep that in mind because it's going to come up again. It also comes up down here, so we get reminded that we have to have that be true, okay? Then with the constant stuff that's left over here, we see that our a1 has got to be equal to 2 plus b1 minus b2, okay? And then on the other equation, we break it out the same way. And then we find out with the constant stuff that a2 has got to be equal to b2 minus b1 and minus 5, okay? So once you've got that, you have to remember, and I drew kind of a jagged line here, a1 has got to be equal to a2. That means this thing and this thing have to be equal. And so we start trying to solve that. I was worried at first that I was going to accidentally eliminate all my variables and just be completely out of luck. But as you go along with this, it turns out that your B2 needs to be 7 plus 2B1 over 2. Unfortunately, there is absolutely no way to choose B1 in order to make B2 nice. So, lacking any other encouragement, I just chose my B1 to be 0 because that would make some of the calculation easier. B2 then turns out to be 7 halves. Once you know B1 and B2, you can take them and find out A1 and A2. And once you have values for those, it's just a matter of writing it all down. So A1, A2, T, so the -3 halves, -3 halves T, and then the 0, 7 halves for the B, and then you put your X sub H on the end there, okay? So the only thing that I feel like I really need to make sure and point out to y'all is that if I had gotten a cosine T there, I mean 7 cosine T, whatever, then I need to be talking about A cosine T and B sine T. Sines and cosines go together because they've got the same root, okay? So make sure that you put both possibilities into your X sub P as you're doing that. All right, this has ran on much too long. I'm gonna go ahead and let you go. I'll see you in class tomorrow. Thank you.